Yeah, so today we're very happy to have Tony Feng, and he's going to give us an introduction to Smith theory. Tony, take it away.
Okay, yeah, thanks for the opportunity to speak. So to say something briefly, Smith theory is about kind of equivariant localization with respect to a Z mod P action where your coefficients also have characteristic P. And I'm actually going to begin with a kind of example of this, motivating example, which is at a kind of lower categorical level than we're really going to ultimately be interested in. But it exhibits a lot of the features which we're interested in. So to set this up, I'm going to let F be some kind of local field of residue characteristic Q, for example, finite extension of QP or Laurent series in FQ. And I'm going to let G be the group of F points of some split radictive group over F, and K a hyperspecial maximal compact subgroup. So feel free to assume that G is GLN of your Laurent series ring, and K is the GLN of the integral subring. So in this situation, you have something called the spherical Heck algebra for G. I'm going to take little k to be my coefficients, and what this thing is the compactly supported functions on G mod k times G mod k, which are invariant with respect to the diagonal translation action of G, and valued in little k. And as we know, this thing has an algebra structure, which is given by convolution. So it involves two things. You basically sum up over possible middle terms of the product. So this is hopefully a somewhat familiar story, but now I want to take a sort of special, take coefficients which have characteristic and special position. So I want to emphasize that in this talk, Q is not a power of P, but instead Q, which is this residue field, has the property that Q minus 1 is divisible by P, where P is the characteristic of my coefficients K. So, so this means that kind of Q is 1, at least in my coefficients K. So for example, we know that there's like the Heck algebra is bound up with beams of Q deformations. And what I'm saying is like, this is a way of specializing Q to be equal 1. Just take your coefficients, which have this kind of special characteristic property. And so what this concretely means is that in particular, that there will be an embedding of a cyclic group of order P into, into, let's say, the group of units of my residue field, which I could think of as the points of GM over FQ. And then I'm going to embed this by the usual regular co-character 2 rho into G. Okay, so I guess I'm now sort of thinking more about the function field setting. But so this thing will act on G mod K by translation. And it's an exercise to see that the fixed points of this Z mod P here are exactly the kind of T to the lambdas for lambda dominant co-character, where this T is the uniformizer. So in this equal characteristic setting or characteristic P setting, it's the thing which was called T before, and otherwise it's like some kind of power P.
Not dominant, Tony?
Or dominant. You're complaining about that lambda should be dominant, is that what you said?
I was wondering, should lambda really be dominant? I thought it was just all T to the lambdas.
But I think some of those are equivalent under like some of those are K translates of each other, right?
Sorry, can we back up? I'm still confused. Go back to the 2 rho embedding there. Sorry, yep. What did you mean?
What's the question?
What is the 2 rho thing?
Rho is the like half sum of.
Yes.
Yeah. So 2 rho is the sum of these things.
Yes.
Positive roots of of the dual
Right.
group of Ij.
And what's the map?
Well, I have a co-character and I'm evaluating it at like a point. So there is a co-character of G.
Okay, so it's mapping to the torus.
It lands in the torus, yeah.
Okay, sorry. All right, I understand.
But I guess what I want to compare this to, the fixed point statement, is that the fixed points of GM acting on the affine Grassmannian for G would be kind of the same thing, T to the lambda, where lambda is in this thing. Maybe I should say, maybe I should emphasize that this is a coset. Or I can think of this as the image of the Grassmannian for T and the Grassmannian for G. Is this okay? Okay. So yeah, proposition here is that so that, as I just introduced, there's this Heck algebra for G with respect to K, and then there's also the Heck algebra for T with respect to its own maximal compact subgroup. I'm going to assume that kind of K and T were chosen compatibly, so that this is that maximal compact subgroup of T, and I'm just going to consider the restriction map. And the claim is that this is an algebra isomorphism onto the W invariance of the target. Okay, so actually it's going to turn out to be that the fact that it's an isomorphism is, or like a bijection, is kind of easy. And the fact that it's an algebra homomorphism is what uses our assumptions on kind of the position of these characteristics. Okay, so let me just simplify notation by taking G brackets G to be this coset space on which the Heck algebra is defined, and T to be the image of T intersect K to G mod K, or in other words, the fixed points of G under this Z mod P action by this exercise.
Sorry, these are notations for what?
Well,
Spaces or?
Oh, these are sets, I guess. Okay, so proof. So as I say, the fact that this is an isomorphism onto the Weil invariance is kind of soft. Like it's just follows from Cartan decomposition that the things which index elements of G mod K, the things that index the orbits of K on G mod K, or index these double cosets which matter in the Heck algebra, are exactly kind of the Weil orbits of what indexes the analogous thing for the Heck algebra for T. So the isomorphism part is pretty formal. And as I say, the thing which is interesting is that this is actually an algebra homomorphism. That's the thing which requires the assumptions on the characteristic. So let's see that. Let's take two elements, H1 and H2, in your Heck algebra. And what we want to do is compare what happens when you convolve them. And then apply this map, which is just restriction, versus doing it in the other order. So this means by definition, you sum over y's in G of H1 of x, y times H2 of y, z. By contrast, if we kind of restrict it and then convolve, then what we're saying is we've got to restrict this to a function of t squared. This is restrict this to a function of t squared. And then we sum only over these things in t. And the thing you're summing is the same, but just to emphasize that you're looking at it a different way, I'm just going to write this here as well. So what's clear is that these things don't quite look, the same, and the difference would be what you get when you sum over things in G but not T. H1, X, Y, H2, Y, Z. And our claim is basically that this is equal to 0. So why is that the case? Well, I can write this as G minus the fixed points under the Z mod P action. That was by this exercise. The fixed points are exactly this thing. And the special thing about the group Z mod P is that it only has two subgroups, two different subgroups. One is the trivial one, and one is the whole thing. And so once you've cut out the fixed points, then on this thing, Z mod P is acting freely. So I'm going to try and group this sum into orbits for this action and see what happens. Okay, so it's typical notation this subject to pick an actual generator for the Z mod P. I'm going to call it sigma, just for notational convenience. And I'm going to observe that H1 of X sigma Y, H2 of sigma YZ, well, X and Z are supposed to be drawn from this thing. So this is the same as H1 of sigma X, sigma Y, H2, sigma Y, sigma Z. And then because by definition, this Heck algebra was kind of invariant under diagonal translation, it's the same as H1 of X, Y, H2 of YZ. So actually, what we're seeing is that the value of this summand over a Z mod P orbit is the same at every point of an orbit. And in particular, since you act freely, it's the same at P different points. So when you add up the value at this orbit, you're just going to get 0. So you could the sum is already 0 when you add up over an orbit, and therefore it's 0 when you add up over all the orbits here. Okay, so are there any questions about that? Cool. So this very simple idea that I have a Z mod P action, I just want to cut up the space, the ambient space, into the free orbits and the fixed orbits is going to be kind of the idea which underlies all the proofs today. So let me just remark that it's an exercise to show that the map in the proposition coincides with the usual Satake transform. The usual one, which works in all characteristics, is given by some kind of integration. Instead of restriction, you integrate over affine spaces, essentially. And yeah, I guess the point is that one can apply the same argument there and see that each affine space which you want to integrate over has kind of a unique fixed point, which contributes to that integral. I would also remark that the proof works in a more general situation where you have some reductive group with a Z mod P action, and then you take its fixed point subgroup for the Z mod P action, you get some other reductive group H, and it satisfies this kind of double coset fixed point property. The resulting homomorphism Heck algebras is called the Broader Homomorphism. It's, as far as I know, discovered by Truman and Venkatesh. And yeah, they have a paper where they study the implication of this for the Langlands program. But the takeaways which I'd like to emphasize from this example are that in the presence of a Z mod P action, this operation of restricting Z mod P equivariant functions with coefficients and characteristic P has special algebraic properties. For example, in this case, acting algebraically on G in response to the chat. Okay, so the restriction of Z mod P equivariant functions has special properties. For example, in this case, it was an algebra homomorphism, whereas when your coefficients are not in this kind of special position, it doesn't have good multiplicativity properties. So this theme is something which may refer to as function theoretic equivariant localization. And also, what we saw here is that the restriction reflects other special structural properties. So in particular, I produced some map of Heck algebras. And it turned out by this exercise, it was the Satake transform. So a priori, the Satake isomorphism identifies with this with K0 of the representation ring of G hat, the Langland's dual group. And here we get K0, the representation ring of T hat. And so I produce an algebra homomorphism of K0s of some monoidal category, but in fact, it lifts to an actual monoidal functor of monoidal categories. So this actually comes from a functor of categories. And this would be true in this more general situation, which I alluded to here for any kind of projected group G and H. So so what we're saying, in other words, is yeah, we have some kind of map of algebras, but it categorifies. And we'd like to explain that.
What's the functor?
Well, in this case, it's restriction along this.
Okay, it's just restriction.
Yeah, that's because of this exercise that it's the usual Satake transform. But yeah, so as I said, with this more generality of G and H, there's a case-by-case proof. For every example, they write down some map of groups and they check that it works, but there's no sort of uniform explanation for why it categorifies. So and that's something which you might want to have. Okay, so in other words, this is a hint that at least in the situations occurring in geometric representation theory, this function theoretic equivariant localization seems to admit a natural sheaf theoretic categorification, and that's what we're going to be discussing next.
So you take, sorry, Raphael, you take a straight restriction. You don't take any, you don't take the action of your automorphism there into
Where?
consideration in the vertical map on the right. You don't.
In this case, you don't have to. No. So
okay,
in
so
these other cases, yeah. In this case, like I say, that,
yeah. Okay. So that's not. So you mean the action on G hat, is that something that I'm a little bit confused there. So G hat, does it still have an action of sigma, or you're not using that? Anyway, does it?
I'm not using that.
You're not using that. Okay. Okay. Thanks.
So yeah, in particular, if you were to, so as this is kind of restriction of functions, if you were to naively start trying to write down what the categorification of this diagram would be, maybe you would start out by saying, why don't we take the natural categorification of the Heck algebra, which is perverse sheaves on the Grassmannian, and we have the geometric Satake equivalence between this and rep G hat, and you have the analogous picture for the torus. And instead of restriction of functions, why not consider restriction of sheaves? Okay, I'm gonna dot this here. But it's easy to quickly see that this is not going to be a good thing to consider. For example, it doesn't really land in the category that we would want. Like we take a perverse sheaf on the affine Grassmannian, restrict it to I don't know, some subset. It's not going to be perverse anymore. And also this functor is not going to be monoidal. So for it's clear that we used Heck algebra picture. We used the special position of the characteristics, and in particular the fact that when you take a function in characteristic p and you add it to itself p times, you get 0. We used that to show that it was an algebra homomorphism. That fact, the analogous fact, is not true for sheaves. You take a direct sum of a sheaf with itself p times in characteristic p, you're not getting 0. So what's clear is that we don't have a priori at the sheaf theoretic level the kind of cancellation properties which made the function theoretic story work. And in order to have them, we would need to take some kind of quotient at the categorical level. So that's my motivation for introducing this thing, which I'll call the Tate category, which is a certain Verdi quotient of the category of sheaves. So the general setup here would be that you have a space Y, and it has Z mod P action. And yeah, I'm always going to be picking a generator sigma for this Z mod P action. And actually, we're going to assume that it acts trivially. Or Y will later arise as the fixed points of the sigma action on something else. So this implies that the equivariant derived category for Y with respect to this action has I don't know, a simple description. It's just the usual derived category with coefficients in the group ring of this Z mod P, which I'm denoting K join sigma. It's because the action is trivial at the geometric level, so kind of the only action is occurring at the level of the coefficients. And in particular, inside here, you have the subcategory of perfect complexes. So this means complexes whose stocks are all perfect complexes over K join sigma. And to remind you, that means that it's represented by a bounded complex of finite free K sigma modules. Okay. So in this situation, I'm going to define the Tate category. Let's call it Tate Y K to be the Verdi quotient of this equivariant derived category by the perfect complexes.
Sorry, this like K, the group algebra is a Frobenius algebra. It's not semi-simple, so it's just free modules.
You mean, are you asking why I'm not saying projective or something?
Yeah.
Yeah, so I think that would lead to the equivalent definition, like because the only projective.
I'm just saying nothing interesting has a bounded complex of finite free modules except for a free module.
Nothing interesting. Nothing interesting in the heart. Is that what you're saying? Yeah.
Anyway, yes, nothing interesting in the heart. Yes.
Right. Yes, that's why. Yeah. In general, I should maybe say projective, but here it would be the same. Okay. So yeah, let me give an example of the kind of weird stuff which can happen when you take these sorts of quotients. Let's even just take Y to be the most simple geometric space of point. Then, well, you have an exact complex in the usual bounded derived category, which is given here. So, okay, so this is exact. On the other hand, these middle two terms are perfect. So they will become zero in this quotient, the K category. And so that implies that K is isomorphic to its own shift by 2. And yeah, more generally, the identity functor is isomorphic to the shift by 2 functor in the Tate category. So, well, we could say that this Tate category is 2 periodic, but it's certainly this is certainly a property which is not enjoyed by the kind of the usual kinds of derived categories that you work with. So it's a bit disorienting, possibly. Let me see. Okay, and I want to emphasize. So this is the formalism. I'm following a paper of Truman. There's a variant which is considered in work of Reich and Williamson, where this if you assume that the Z mod P action extends to a GM action, then they consider something which they call the Smith category of the fixed points. Oops, okay. Which would be the GM equivariant derived category on the fixed points modulo complexes whose restriction to the Z mod P equivariant derived category is perfect over K sigma. So I'm kind of quotienting out by things with the same condition that they're perfect when you regard them as Z mod P equivariant sheaves. And for them, this happens because they're considering the loop rotation action on the affine Grassmannian. And then inside here, of course, there's a mu P or Z mod P. So in their situation, this Z mod P action does have the property that extends to a GM action, and they can find this category. And it's a kind of technical improvement, at least for their purposes. Okay, so yeah, maybe now's a good time to take a break.
Yes, sounds good. Let's meet back at 3:32.
Are you going to be talking about the monoidal structure soon?
What structure?
Monoidal?
You mean like in this kind of Hector context, or in a more naive context?
Well, so suppose Y is a point, for instance, right?
Yep.
I'm just trying to figure out, like, presumably you're using the standard Hopf algebra structure on the group algebra?
Yeah. But okay, so the monoidal structure, it's going to be over K. I'm going to tensor over K. So that there'll be no kind of subtlety about it.
Yes.
Yeah.
But there's sort of two different natural Hopf algebra structures on the group algebra, Z mod PZ and characteristic P.
Okay.
Confirming that you're using the standard one.
Sure, I'm using the standard one. So you're referring to like how, if I take two Z mod P modules, how do I make them their tensor product into a Z mod P module? And I'm doing it in the standard way. Yeah.
Okay.
Diagonal way.
Can I actually ask about this this thing with the extending to the GM action? So, so the cases where I'm kind of familiar with this is like you have, like if you had a finite group acting on a variety and then you study its you look at the L-adic cohomology, then, I mean, normally what happens is if you have that finite group, if that extends to the action of a connected group, then the action is kind of really uninteresting.
Right.
Like, and so I'm kind of trying to see why do interesting things happen here, but not in the situation I'm familiar with. Why do you want that? And normally you don't want things to be in a connected group action. That's normally the way I think about things. So I'm just kind of wondering why you want that here.
Mm. I mean, yeah, that fact is kind of a consequence of working at a lower categorical level, I guess. So cohomology, I don't know, one way of thinking about that fact is like cohomology is like a discrete thing, and then if you have a continuous thing acting on a discrete thing, then of course it's trivial or connected. Whereas, yeah, this derived category, certainly not a discrete thing, so it's reasonable to have a connected action on it. That's a very lowbrow point of view. My lowbrow point of view on kind of why the cohomological action is trivial and this kind of categorical action is not trivial.
Maybe to answer. Yeah, I have had the same issue in the past, so maybe I can reply to Jay. So the cohomology will have a trivial action of your finite group because the action extends to the action of a connected group. But now, if instead of computing, say, cohomology is X from the constant shift to itself, now what you can do is instead compute the X in the equivariant category. And that's going to be very different, as that's really going to use the, yeah, I mean, this is not the same as the X in the non-equivalent category. So that's where there's a subtlety. You really have to move to the more equivalent derived category. If you stay with sheaves, with equivalent sheaves, that would be really interesting. As you said, Jay, there would be nothing, I think.
Okay, that makes a lot of sense. Okay, thank you. That's very helpful.
Can I add something? It's Daniel. Can you hear me?
Yeah.
Yeah. So we'll see next week the application to the linkage principle. So if you take GM fixed points, you will have, there will be this Smith functor which goes to sheaves on, some kind of sheaves on the fixed points. But if you take GM fixed points, you will have infinitely many components, which are finite flag varieties. But if you take mu p fixed points, you will have, it will reflect the block decomposition of the linkage principle. It's only finitely many components, which are, again, infinite dimensional. So it can be really useful even if mu p is a part of GM, and it's also easier. So we will see this. Yeah.
Well, I look forward to tuning in next week.
Okay, I think we can start back up.
Great. Okay, thanks. So I'm going to take a little bit of time to discuss, like, what are perfect complexes? Like, how do they arise in geometry? So there's a few situations where you can recognize them. And one is, suppose that you have a space which has this, I'm just going to start calling it sigma action. I think it's abusive notation for Z mod P action, where the Z mod P is generated by a thing called sigma. So suppose you have a space where you have a sigma action which is free, and you had an equivariant sheaf on it. Then a little lemma says that then the cohomology of the space with coefficients in any such sheaf is perfect complex. And you can think of this as a kind of categorification of the exact argument we choose, which we used earlier. Earlier we were talking about if you add up a function over a set where Z mod P acts freely, then you can group it into orbits, and that sort of sum will be 0, or the integral will be 0. And in this categorical setting, these perfect complexes are the ones which I'm thinking of as being 0 because they're kind of summed over orbits. And what we're saying is cohomology, which is like the categorization of adding up a function, is perfect as long as the space is acted upon freely. And the proof will also be along the same lines. So what we did before was we said, let's group a sum into orbits. And here we're going to do that. We're going to collect the orbits by just considering the quotient from my space X to quotient by that Z mod P action. So cohomology could be thought of as the push forward from X to the point. And I'm going to first consider pushing it forward along orbits. And so the cohomology of X with coefficients in F is the same as the cohomology of X mod sigma with coefficients in that push forward sheaf. And now a crucial observation is that this thing is already perfect on this quotient space. Because, well, this map from X to X mod sigma, the action was free, so this is a Z mod P torsor. And over every point, the fiber looks like a principal homogeneous space under Z mod P with the translation action. And so your sigma is already acting freely on the fibers. And so the stalks of this push forward pi lower star F are just some kind of induction up to sigma from the trivial representation, or one can sort of visibly see that Z mod P is acting freely on it. Okay, so then the statement we want reduces to another lemma, which is that now let's say we have a Y where sigma X trivially, and a complex F, which is perfect on Y, then cohomology of Y with coefficients in F is already is perfect.
Can I make a comment, Tony? So
yeah.
The proof above, there's one more step. It's the fact that if the Stokes are perfect, then the whole the complex of sheaf is perfect, because your definition was not that the Stokes are perfect for this thing. The Stokes being perfect means that the it's a sheaf of if you go back, what you call perfect of there. Oh no, that's your definition. Sorry.
Yeah, my definition is
the definition Stokes. Okay, I see. So your lemma will be to show that the definition is equivalent to one where you ask conditions about every open set or something like that. That's an equivalent. Okay, now I see. That was you have two ways to define this subcategory. You can define it for the Stokes, or you can define it, which is weaker conditions, and asking that say you have a complex of in the category, say, of projective K of sigma modules, or you have various ways to express that. But the two are equivalent, and that's probably implicit in the lemma. Maybe in the proof of your next lemma that will appear.
Yeah, we can see, but yeah, for now, let's say my definitions are all pointwise.
But your definition is pointwise, okay.
But sorry, I forgot. I actually wanted to, before continuing with the proof, I wanted to draw a proof by picture of this lemma, because if we permit ourselves at least to work in the topological context, topological spaces and singular cohomology, then it's actually fairly obvious. And we'll call this one 2. Because the intuition is just that we could just choose a triangulation of our space X, which is acted on by sigma. A triangulation preserved by sigma, and then the chain complex, which computes the cellular homology, is itself already a perfect complex. So, and that's because every cell, the cells are. Oh, yeah, sorry. I guess the picture should kind of omit this point. Because the space was acted upon freely, I can choose a triangulation which is permuted freely by my group, and therefore the actual cell complex is sort of visibly a perfect complex over K sigma. So that's meant to be kind of a picture which makes it intuitively obvious, at least in the topological situation. Sure. Okay. But okay, so going back to the proof, actually there's something simple here, which is the claim is that, well, F is, so by devisage, reduce to F being a sheaf, so in the heart. That's because I can just filter any complex by the terms in it, and I've assumed that there's a representative for which the terms are free, finite free. And then once it's a sheaf, that implies that F has to be induced. And yeah, concretely, F0 should be just defined as the sigma invariance on F. So there is a natural map. You can check on Stokes, that's an isomorphism, and on Stokes, you check that by inspection. And so that implies that the cohomology is also induced. And so it's sort of visibly finite free, visibly a perfect complex. Okay, are there any questions about that?
I just wrote in the chat that I'm sure that that's okay when you have some constructibility assumptions, but I'm not sure without constructibility assumptions.
Oh yeah, I think it's actually, yeah. So to be clear, every time I'm talking about derived categories here, I'm talking about constructible derived categories.
So can I ask you, how do you do the devisage? Because your assumption is the complex of Stokes is perfect. I'm a little bit confused. What do you mean by dévissage?
What I mean is like, so I yeah, I see. This is probably where we need that lemma that you mentioned, right? That kind of.
Yeah, there's something. I think there's something non-trivial in there, and it's the fact that, I mean, if you, the best you're going to, I don't think you can prove better than the fact that the global sections or whatever, that this is flat. But flat implies is going to imply projective. So you're good. So somewhere I think you will need I mean, I don't know a proof along the lines that you're giving. Maybe there is a proof, but I can see only a proof. So the standard proof would be to say that to use the base change formula and to prove that your push forward has finite Tor dimension. Okay.
Yep.
When you take Tor, and finite Tor dimension will imply perfect. So that SGA proof, standard, whatever, Dunning proof.
Right. Yeah. So as Raphael's mentioning, there's another characterization of perfect complex in terms of finite Tor dimension. But okay, once I know the stocks are perfect.
Maybe there's a simpler proof. So if a stock, if you have if you work in the derived category of constructible sheaves over some ring of coefficients, if the stocks are perfect, the only thing you're going to be able to deduce is that sections are flat. You're not going to. It's not true that the stocks are the global sections are perfect in general. Okay, that could fail. So somewhere you. So maybe there's a way using fixed points like you do to get it to get a better proof. But if you replace K of sigma by any algebra, any ring, you have to be careful. If your ring is a finite dimension, if you replace K of sigma by a finite dimensional algebra, then it's okay. The result is true.
Yeah, what I have in mind is like spreading out the statement from stocks to open sets by using this, like take invariance that produces a map. Spreads out.
Maybe one can do it like that. Absolutely.
Yeah, it's a good point. Yeah, I should think about that. All right. So now we're moving on to the Smith operation, and this is going to be a kind of sheaf theoretic incarnation of this like miraculous restriction that we saw for functions. So one thing which if you have this function sheaf dictionary in mind, one thing that's already making you nervous is that although there's only one way to restrict a function, there's kind of two ways to restrict a sheaf. So I could contemplate either like a star restriction or sheaf restriction, not the same, of course. So let's let F be an equivariant sheaf. Okay, and so what is the difference between them anyway? So I'm going to contemplate this cone. Okay, so we have this exact triangle in the equivariant derived category. J here is the inclusion of the complement of the fixed points, the open inclusion, and I is the inclusion of the fixed points. And in particular, if I then apply I upper star, then, well, it's still going to be exact, and it's going to be an exact complex in equivariant derived category of the fixed points. And I guess you can sort of ignore this. Doesn't do anything. And so we have a canonical map from I upper streak to I upper star on here. And the proposition is that the cone of this map is perfect. And so in particular, that means that the map becomes an isomorphism in the Tate category. And yeah, so well, we already kind of know what the cone is. It's given by this thing. So we basically want to say that this thing is a perfect complex. And so we want for all fixed points y, this stock to be perfect. And what is the definition of this anyway? So this is some kind of a limit over neighborhoods of my point of crucially the cohomology of the open set intersect that neighborhood. So U intersect X minus X sigma. And I can, by taking intersections, I can consider only the cofinal system of neighborhoods which are themselves stable under the sigma p action, the sigma action. So sigma, I can assume acts on this. And so this is inside the complement of the fixed points, sigma's moreover acting freely. So this is a case of taking cohomology with coefficients of a space where sigma p acts freely. And okay, so essentially the arguments we gave before can be used to show that that it's perfect. Yeah, so as I say, therefore, these two compositions, although they differ, these two restrictions, although they differ, they become the same in the Tate category. So the upshot of this is that two compositions agree. The star restriction and then projection to the Tate category, or the streak restriction and projection to the Tate category. And so we're going to call this composition the Smith operation. Which is called PSM or I upper shriek star, to emphasize that it's like kind of both the shriek and the star. And let me just make a comment about one reason this is important, that these two things are the same. I mean, now, well, it means there's a canonical restriction map, but from a technical perspective, as we know that there's classes of important sheaves in geometric representation theory, for example, the perverse sheaves and the parity sheaves, and these are defined by conditions on star and shriek stalks. And this means that if you star restrict, usually you would lose control over shriek stalks, and star restriction of a perverse sheaf is not going to be perverse. When you shriek restrict, you lose control over star stalks, but you retain control on shriek stalks. And now, since kind of they're the same thing, we have control over both star and shriek stalks, and this ultimately allows one to prove that like this Smith operation retains good behavior with respect to parity or perverse sheaves. Okay, and let's see. There's an analogy to keep in mind between what we're discussing, which is like a Z mod P acting on a space X and torus acting on a space X. And in this analogy, one can think of this Smith operation as being analogous to hyperbolic localization. And this thing is some sort of confluence of the shriek and star pullbacks. The other thing is also some kind of combination of shriek and star pullbacks. I think because of time concerns, I won't say more about this right now. So I want to move on to explain a kind of sixth functor formalism for this Tate category. Okay, so let's see, maybe I can condense this somehow. So Verdier duality, which is the functor which takes f to R hom, okay, f omega y, where y is a space on which your Z mod P is acting trivially. This can be upgraded to a functor of equivariant sheaves, and then it preserves perfect complexes. So yeah, I guess a comment here is that our things, we could consider the sheaves over K the group ring of Z mod P, but we don't want to do that. So if we take R hom over K, then it'll certainly send a free thing to a free thing, and it'll still have an action of sigma in particular, and so it preserves perfect complexes, and that means that it descends to the Tate category. Same discussion applies for the monoidal tensor structure that Ben brought up earlier. So if you just take tensor products over K, equip it with the diagonal sigma action, then if one of the sides is perfect, well, as soon as you tensor like a free representation of a group with any other representation, it's still free. So perfect complexes form a kind of ideal with respect to this operation, and that descends to give a monoidal tensor product on the Tate category. Okay. There's also a pullback operation. So if you have a map of spaces with sigma action, which is equivariant, let's call it F. Then, so it will pull F upper star will pull back perfect complexes on Y to perfect complexes on Y prime, just because F upper star interacts really well with star stalks. So we're going to get F upper star from the Tate category of Y, the Tate category of Y prime. And then since you have Verdi duality, you can also define F upper shriek as well. So the theory of pullback is pretty simple. And finally, let me discuss push forward. So we consider the same setup. And to know that the push forward will descend to the Tate category is to know that it preserves perfect complexes, so that it extends to a map of quotients. And so the claim is that our F lower shriek sends perfect complexes on Y prime.
Are you assuming the actions are trivial here? No.
Yes. Two perfect complexes on Y. And yeah, this is again a condition, as I've defined it, a condition on stocks to be a perfect complex. So to check that the image R lower shriek of a perfect complex is perfect, I can restrict to a point, and then I can use proper base change. And it becomes, so basically proper base change allows me to reduce to Y being a point. And this is essentially something we already saw. Cohomology of a perfect complex is already perfect because the sheaf itself, like the cohomology is induced up from cohomology of something else. The only comment is that here, because we're talking about complex supported cohomology, it's not technically the same statement as I wrote earlier, but the same proof works. So the statement is that complex supported cohomology, such a thing is perfect. By same argument. Okay, so the last thing I want to do is just discuss some compatibilities of these operations with the Smith operation, Smith restriction. And yeah, a slogan which I learned from Jordy was like everything commutes with the Smith. You can remember these statements as everything commutes with the Smith operation. So for example, for duality, Verdi duality, the statement is that if I start in the equivariant category and I apply Verdi duality, and then I apply the Smith operation, that's the same as first applying it and then applying duality. This is almost tautological the way we define. I mean, we define duality at the take category to be the descent of duality upstairs. The only comment we need to make is that, so this is almost tautological, except, so let's say we define the Smith operation by using upper star and then projection to the take category. Then the dual would take that to some sort of upper shriek, because the dual of upper stars is upper shriek. So a priori, there's some interchanging of shrieks and stars, and what makes this work is that, so there's no problem because they end up being the same. Once you pass to this take category quotient. So that's the only content to this statement. Similarly for pullback, so you have a sigma equivariant map. Then the statement is that if you pull either shriek pull or star pull, all my operations are derived, by the way. Should have probably mentioned that earlier, but either pullback commutes with the Smith operation. Oops. And this is sort of similar reason to before. It's basically, it's almost tautological. We define the Smith like the Smith pullback to be, the pullback on take categories to be a descent of the one kind of upstairs. So the statement here is that, like, if I think of the Smith restriction as like upper star, then of course it commutes with other upper stars. On the other hand, if I think of it as upper shriek, it commutes with other upper shrieks. So because it is both, it kind of commutes with both operations. And finally, something which has a little bit more content, although we've already seen the content, is that if I have a push forward map, then, so actually I may as well, I'm going to write this differently to emphasize it. I may as well just assume that sigma is acting trivially here on S, because if you think about it, the statement will kind of always reduce to such a case. And the statement is that the push forward at derived categories at the level of derived categories commutes with the Smith restriction. And just to say a word about the argument, so this is the thing which we've seen several times now, where this is basically saying that one way, this is sort of like taking cohomology, this vertical arrow, a relative cohomology, and this one is taking relative cohomology of the fixed points, and saying that the same is some effect saying like cohomology of a thing is the same as cohomology of its fixed points. And the argument is that you can cut it up into fixed points and free orbits, and the free orbits contribute nothing, or at least something perfect, which becomes zero in the take category. So the idea would be that I can compare.
You keep saying things like this, but you're talking about a case for sigma x trivially.
Well, on S, sorry.
Oh, okay.
Yeah.
Was that the same thing earlier? Okay. You were only assuming the action on Y is trivial.
Earlier, when I was talking about sending perfect complexes to perfect complexes, then the action had to be trivial. Otherwise, it doesn't make sense. But in this compatibility section, we never, things were not trivial up until this point. Maybe I can just quickly say what I want to say here, and then we can revisit that question if we want to. So the idea would be, I want to compare kind of the sheaf with its restriction to the fixed points. The complement is kind of the sheaf on well, the complement of the fixed points where the action is free. And so you can then apply F lower shriek to everything, let's say. And you would see that this part is perfect. And so that says that these two things become the same in the Tate category. And yeah, that's the idea. So, so this is the kind of six-functor formalism and compatibilities with this kind of exceptional or miraculous Smith restriction functor. And let me stop on that note. Thanks for your attention.
Any questions for Tony?
I have a lot. As usual. I guess my first question is a hard one, so it's for the audience. What happens to this story if you use the other Hopf algebra structure on the group algebra to define the monoidal structure and perhaps push forwards and so forth?
What does that mean concretely? So you're just talking about a different way of turning like M and M or ZP representations. And the question is, what is the ZP action on here? And what is the one you're proposing?
Right, so normally sigma, you're having sigma act by sigma tensor sigma. Right, but if you think about sigma minus one as being this nilpotent thing, and instead you think that sigma minus one's like in a Lie algebra. So you have sigma minus one act on the first factor plus acting on the second factor. And if you compute out what that says that sigma does, you sort of have an extra, it's a little bit different. So sigma acts as sigma on both factors minus sigma on the first factor minus sigma on the second factor or something like that.
Okay, you're saying
I'm not 100% sure, but yeah, that's right. So I mean, it's the same ring. So what it means to be perfect is not changed.
yeah, but does this one have the property that perfect tensor anything is perfect?
Yeah, that's true for any Hopf algebra. Any finite, yeah, any Hopf algebra. Does anyone know, like, what changes?
I mean, I think that it's just so sure. You've got this Hopf algebra, and you can consider sheaves of modules over it, and you can take tensor product. But the real interest in Smith theory comes from the fact that you have this group action and you've got fixed points. Whereas this Hopf algebra, I don't know what it would mean to kind of.
It's the same group. It's the same group algebra. I mean, you've got a group action. It's the same algebra. The only thing you change is the coproduct.
I think what Jordi mentioned, Ben, is that starting from a finite group action on a variety, you get an action, some of the group algebra on functions on your variety, which is compatible with the multiplication in the Hopf sense. But now, if you change your Hopf algebra structure on your finite group algebra, this will not hold anymore. So what you're saying is that you're starting with a finite group, with a group action on your variety. Once you take a quotient or something like that, I mean, then you have sheaves with values in this algebra, but you're going to lose this strong fact that will be true only for the group coproduct on your group algebra.
And this multiplication of functions being compatible, that's like, so it's coming into play when you take convolution or push forwards or something.
I mean, I don't know, but it's somewhere. It's yeah, there are places where you use that.
Right. No, that makes a lot of sense.
Ben, isn't that Hopf algebra with the different coproduct? I mean, isn't that essentially like the Frobenius kernel of the additive group? So like,
that sounds right.
it should be like almost like you're trying to do Smith theory, where you have an action of the Frobenius kernel on something rather than the cyclic group.
Right.
I don't know that really makes sense, but that seems like what you're suggesting.
Cool. Thank you. Sorry, I was just really curious.
So Tony, I was just thinking, like, I'm still really interested by your example at the very start of the talk. This kind of, so you're saying it's the Satake transform, but it's like the mod P reduction for your particular P of the Satake transform.
Yeah, coincide. Yeah, I guess I think of it as like it coincides with the reduction of the Satake transform, but maybe philosophically should be thought of as being different.
And I'm just wondering, like, you could kind of imagine that we didn't have the Satake transform, then you could make it by kind of saying that if you know something mod P for enough P's, then you can kind of piece it together.
Yeah, well, unfortunately here, to make this thing work, you have to assume P is pretty small relative to Q. So for a fixed Q, you don't have enough to lift it to characteristic 0. But that trick is what I'm using on the other side when I gave this talk about this commuting variety. Like if you fix the Langlands dual group, then for each P you can choose a Q which works, and implement an argument on the Heck algebra side.
And I get the other kind of just technical thing is that the fixed point statement is only true, like it'll fail in small characteristic, I guess.
Maybe characteristic 2, but actually yeah, sorry. Will it fail? Yeah, okay. Characteristic 2 is definitely going to be a problem, but
no, but I think if your root compares against like any number that occurs as a pairing of 2-row check and a root, will give you issues. So it won't just be characteristic 2.
Oh, okay, you're right. There, in small characteristics, there's some cases where it won't work. Yeah, so good point.
And I kind of wonder if, like, it might be interesting to know what actually happens there, but I can't see it at the moment.
Right. Yeah, I like to advertise this question of giving an explanation of why it categorifies, because I say I think that answers to this question will be useful, like in Langlands functoriality. So, hoping some representation theorists will come along and explain it.
Any more questions for Tony?
Oh, but maybe just, sorry, Mackie, can I just so that everybody has a rough idea where we're going. So there'll be 4 or so lectures on Smith theory in the working seminar. And then the idea is to go in the direction of 2 realizations of the affine-Hecker category, as I've said repeatedly last term. The other themes that we would like to pursue this semester are some discussion of the kind of billiards conjecture and just some explanation of what's going on there and where we're stuck. And also Roman suggested to have some kind of mini seminar, and I'm not sure how extensive it'll be, on microlocal perverse sheaves, which I think is a great idea and I'm excited about. and if you are particularly interested in one of those directions and would like to give a talk, let one of us know, either Mackie or Roman or Raphael or Jay or me. So, yep, that's a rough summary of where we're headed this term.
And I also
the SL2 seminar.
Sorry?
Is there still going to be the SL2 seminar this semester, or is that over?
Yeah, so we decided that it'll morph into an SL3 seminar. And we'll discuss billiards and things like that. But there are still some loose ends from the SL2 seminar that we'll try to cover. So it'll be some kind of SL epsilon seminar where epsilon is somewhere between 2 and 3.
There was a comment in the chat about relation to classical Smith theory. So yeah, actually, so for example, there's this push forward compatibility at the end contains where is it? Contains a certain equivariant localization statement, which I think is equivalent to the kinds of ones that you find like in Quillen's paper, cohomology of equivariant spectrum of equivariant cohomology ring. Like here, if you take, this is something, you take S to be a point. What we're saying is that kind of compactly supported cohomology of X is isomorphic to the compactly supported cohomology of the fixed points in the Tate category. And maybe a better way to say this is that this implies, so yeah, this implies that Tate cohomology. Okay, sorry, I think. Before that, maybe say there's a, yeah, and this analogy between equivariant localization for torus actions and Z-mod P actions, there's this kind of familiar story we have here where cohomology of X, equivariant cohomology of X is the same as cohomology of X fixed points, equivariant. Or you can think of this equivariant cohomology as a kind of Arham in like an equivariant derived category. So there's a thing called Tate cohomology, which plays the role of equivariant cohomology.
I mean, if I may interrupt, I think Tobias' question is one basic result of Smith theory is that if you take a space which has a cohomology of a point, and you take mod P, and you take a fixed point by an automorphism of order P, then the resulting space still has a cohomology of a point. That's a basic result of Smith theory. I think that's what
Right, exactly.
Tobias is referring to, this type of results. So I mean, you can, I mean, I know that, I mean, this is something, so you can see, you have a functor which goes from, I mean, the idea is that the complex of chains from X, out of that, you can get a complex of chain for the fixed point space, not by applying fixed points component-wise, but by doing some this other, what you call Brower type construction, where you take basically image of fixed points in co-fixed points. So this way, you're going to have a functorial way to get, when you have some more functorial way to get from things with an action of sigma to things with no more action, but you're not quite taking fixed points. So that I think that fits with what you have said, but it's a slightly different direction.
So yeah, I think maybe you're referring to like, if I take the chain complex for X and I apply Tate construction.
Yeah, then you will get a complex of chain for fixed points. Yeah, exactly.
Right, you get exactly the chain complex with the fixed points.
Exactly. Yeah, so I think this is how you can connect back to original Smith theory.
Tate construction.
Another way of saying this in the kind of in exactly the language of Tony's talk is that, so another reformulation of what Smith initially showed is that a Z mod PZ action on something that's a P Poincare duality space is a P Poincare duality space. So if you have a space in which the links of every point look like a homology P sphere, then taking fixed points preserves that. And that's the same thing as saying that the constant sheaf is self-dual up to a shift. And basically the commutativity of Smith restriction with duality tells you that if you take a space on which the constant sheaf is self-dual up to a shift, then the same will be true on the fixed points, which gives you the the fact that you get a P Poincare duality space.
Somehow Smithsyria is about a whole bunch of results, and I guess you can ask about how many of these more topological results you can prove in this algebra geometric world, right? So, you know, like there's both the acyclic being acyclic, but there's also the thing about, you know, the various bounds in the Bethe numbers and the fact that spheres localized to spheres and things like that. I don't know how that.
I think most results. I mean, most of those I know do. I mean, all I think those I know do. Yeah, come as can be proven in this type of manner. Yeah. At the end, it's you have a I mean, you want to say if you have a complex of permutation modules such that the cohomology has this and this property, after you apply the TET construction, then this and that. I mean, that's a type of, and I don't think it always works. I forget who that, I mean, maybe Serge Book or someone like that once told me of something that didn't work, but most things, I think, most basic things can be proven like that.
Right. I mean, many things are just facts about like functors on the orbit category, right? You could look at the orbit category of Z modulo P, and then you can prove many of these things. But I guess, you know, if you somehow want more structure than just knowing things about cohomology, right? So.
Yeah, so you can work in the category, instead of looking at the RAF category of sheaves, for example, with a sigma action, you can look at, I'm thinking of working on the quotient category. You can look at complexes of sheaves such that the Stokes are actually permutation modules. And so there you have a much finer invariant. So sometimes you can prove things using this finer invariant rather than just an object of some equivalent RAF category. That's also a way to get more.
Just a comment that I found really interesting was, so somehow I feel like in geometric representation theory, we're kind of extremely used to the localization theorem for a torus action, like a GM or a algebraic torus, but somehow we're not so used to Smith theory. And so we kind of have this illusion that equivariant localization for tori is somehow the basic thing, and then we kind of say Smith theory looks a little bit like torus localization or hyperbolic localization, but it's a bit weird. But what Truman pointed out to me is that Borel, when he started developing equivariant localization for tori, was heavily motivated by Smith theory. And he actually uses Smith theory and choosing like bigger and bigger cyclic groups for his first proof of the localization theorem.
It's amazing.
Yeah, and if you want to do it like for these p-compact groups or something like that, that's how you prove everything for tori. You prove it for Z modulo P, and then you extend to larger and larger cyclic P groups, and then you pass to the limit. So there, you know, Z modulo P is all you got sort of to start with, and there you also have this amazing theorem of Dwyer and Wilkinson, which says that you can actually not only, you know, you can find a functorial way of describing the cohomology of the fixed points in terms of the equivariant cohomology. So there's a formula in terms of the Steenrod algebra and things like that, which simply gives you a formula for the homology of the fixed points, the cohomology of the fixed points from the cohomology of the Brill construction of the whole space. So you have to look at this, take the largest unstable algebra over the Steenrod algebra. So you do this, look at the Brill cohomology, you invert something, then it won't be an unstable algebra, so it won't look like the cohomology of the space. Then you take the largest subalgebra inside there, which looks like the cohomology of the space, and the result is that this algebra is basically the cohomology of the fixed points. So it's completely sort of like it's a closed formula for the fixed points in terms of the equivariant cohomology of the whole space.
Where is that? I don't know that. Where is that explained, for example?
So it's a short paper in the Annals from the 80s called Smithsyria Revisited. And many of these things also are subsumed in all the theory about the T functor, because where it's formula which holds more generally for homotopy fixed points.
I see. So that's Land's. That's the theorem of Land that tells you that.
Yeah. So the original paper of Dwight Wilkerson is just sort of basic calculations with the T functor. You don't need to use Land's T functor, but what they're constructing gives another interpretation of what the T functor actually does to cohomology of a space. It can also be interpreted as sort of a localization type thing.
So does it mean, normally you would expect, like what we still have on the slide, that you need not just a cohomology, but you need more. You need the complex, you need some information about higher structure or infinity things. But in some sense, what you're saying is that instead of using this higher information, somewhere non-formality or whatever, this is somehow the Steenrod algebra is precisely there to supply this missing information. So there's something like that going on. Is that?
Yeah.
Oh, that's amazing.
Yeah. So the Steenrod algebra sort of, supplies information that you would not. Yeah, that you think would sort of be encapsulated in the higher structure, and would also not be true. This, like the formula, this cohomology formula would not be true for general cyclic groups, for instance. It's something which is particular to Z modulo P, and it boils down to the theorem of Lahn, which says that the cohomology of the mapping space of maps from the classifying space of Z modulo P to any space X, has this formula in terms of the T functor. So it can be calculated functorially just from the cohomology of X together with all the Steenrod algebra operations. So yeah. So no, right. So there's not, I don't know if it's quite where so it says that no sort of like deeper structure is sort of needed, which is very strange, and it comes down to this algebraic fact that if you look at cohomology, then the cohomology of the classifying space of elementary abelian groups has this weird property that is an injective object in the category of unstable modules over the Steenrod algebra. So it has this extra algebraic property which makes all sorts of spectral sequences just collapse. So this is, and this was sort of not obvious to like Brill and these people, but it could sort of be formulated back then, but it was then discovered in the 80s by Carlson and Miller. Yeah, so that's the whole story there. Yeah.
So you're saying I can compute the cohomology of the fixed points from cohomology of the actual just the X plus Steenrod action?
No, the equivariant cohomology of X.
Equivariant, like
Right.
this.
So right. So the localization theorem would tell you some sort of connection that they were the same after inverting something, but this says that you can actually recover the left hand side from the right hand side if you also give yourselves a Steiner algebra action.
Cool.
Yeah, excellent. Yeah.
A similar thing to this happens with maybe I'll talk about this later if you want to stop things.
Yeah, maybe I will stop the recording now, and then if people want to stay in chat, that's still okay. So let's thank Tony again